All right. So let's move on to 9.3. In 9.3, so we're going to talk about infinite series here, and this is going to be the topic of discussion for the rest of the chapter. Really, is infinite series. So let's get into it. All right. So an infinite series is an expression that can be written in the form, you know, it's a sum from k equals 1 to infinity. But the key here is that, you know, there is no kind of upper bound on the sum. It's just an infinite sum, right? So basically an infinite series is an infinite sum. And these numbers, you know, the u sub k's, are called the terms of the series. Now, at first glance, it may not be totally clear the difference between a series and a sequence. So let's just make it crystal clear, right? A sequence is just a list of numbers, right? So a sequence is just a list. A series is a sum. So like if you add up all the terms of a sequence, that's when you get a series, okay? Colloquially, right, in English, we use these terms interchangeably, like, right, sequence, series. But in math, they mean very different things, right? A sequence is just a list of numbers. A series is a sum, right? So you're adding up the numbers on the list. Another thing that may seem kind of silly about this at first glance is that, well, if you're adding up infinitely many numbers, aren't you just going to get infinity every single time? And the answer is no. Oftentimes, yes, the sum of an infinite number of numbers is just infinity, right? But sometimes sometimes it like bounces around and does weird things, and sometimes it converges to a finite sum. And to give you a really clear example of that, just consider 1/3, right? We can rewrite 1/3 as this infinite decimal, right? 0.33333 going on forever. Well, we can rewrite that decimal as 0.3 plus 0.03 plus 0.003 plus 0.0003 and so on. And so right there, you've got an infinite sum that obviously converges to 1/3, right? We could take it a step further, I suppose, and rewrite 0.3 as 3/10, 0.03 as 3/100ths, 0.003 as 3/1000ths, and so forth, okay? And so we can rewrite that in summation notation as follows, right? So it's the sum from k equals 1 to infinity of 3 over 10 to the k. So here we have an infinite sum that clearly is equal to a finite number. So yeah, you can add up, sometimes under certain conditions, you can add up infinitely many numbers and still end up with a finite sum. And in fact, this finite sum is not even that big, is it? So, okay. But this sort of raises the question, you know, when does an infinite series converge to some kind of finite sum? So to answer that question, we're going to look at a sequence of partial sums. So let's give this definition. And by the way, there's like a lot of definitions here. It should go without saying at this point that, you know, you can pause the video, copy down the definitions, copy down the things that I'm saying if you think you'll need them right later on. But anyway, I'm just gonna kind of forge ahead. Okay, so definition, right? So for the series sum from k equals 1 to infinity of u sub k, let s sub n be the sum from k equals 1 to n of u sub k, right? So s sub n is just the partial sum because we're only going to add up the first n terms. Instead of adding up all infinitely many terms, we're just going to add up the first n terms and call that thing s sub n, right? So s1 would just be u1. s2 would be u1 plus u2. S3 would be u1 plus u2 plus u3 and so forth, right? Sn would be u1 plus u2 plus u3 all the way up to un, okay? So this number here, Sn, we're calling that the nth partial sum of the series. And the sequence of partial sums, right? So the sequence Sn from n equals 1 to infinity is called the sequence of partial sums, okay? So let me give you a concrete example using 1/3 again, right? So here's 1/3 written in kind of a fancy way, I suppose. And S1 would just be 3/10, which we can write as 0.3. S2 would be 3/10 plus 3 over 10 squared, okay? Which, if you add that up, you get 0.33. And S3 would be 3/10 plus 3 over 10 squared plus 3 over 10 cubed, which is 0.333, and so forth. So the sequence of partial sums would be 0.3, 0.33, 0.333, 0.3333, and so forth. Okay. So now how does this help us determine if a series converges or diverges? Well, the series is going to converge or diverge if the sequence of partial sums converges or diverges. And in this case, you can tell that this sequence of partial sums is going to converge to 0.3 repeating forever, right? In other words, 1/3. This sequence of partial sums converges to 1/3, and therefore the series converges, or the series, right? So the sequence of partial sums converges to 1/3, and therefore the series converges to 1/3, right? So that's what we're saying in this definition here, which you should definitely write down. This is hugely important, right? But let S sub n be the sequence of partial sums of this series, sum from k equals 1 to infinity of uk. If the sequence converges to S, then the series converges to S. And S is called the sum of the series. If the sequence diverges, then so does the series. Okay? So if the sequence of partial sums converges, then the series converges. If the sequence of partial sums diverges, then the series diverges. So we're going to use that definition to determine whether the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 converges. This, by the way, everything that we're talking about in this chapter has a lot of historical context that is really, really interesting. If you're interested in any of this, you should look up convergence and divergence. Like maybe I'll post some videos that you can just kind of watch for fun. But yeah, this series in particular has a lot of historical context. Some of the geometric series we'll be looking at has a lot of historical context. But anyway, let's get back to the task at hand and determine whether this series converges or diverges. So we have 1 minus 1 plus 1 minus 1 plus 1. Say minus 1 plus, etc. Okay. So to determine if the series converges or diverges, by the way, if you wanted to write out the summation notation for this, we could write it as sum from k equals 1 to infinity of -1 to the k plus 1, right? So it's that sum. And if we want to figure out if this thing converges or diverges, we're going to look at we should look at the sequence of partial sums, right? So the sequence of partial sums would look like this. S1 would just be 1. S2 would be 1 minus 1, which would be 0. S3 would be 1 minus 1 plus 1, which would be 1. S4 would be 1 minus 1 plus 1 minus 1, which is 0. Okay, and so forth. So the sequence of partial sums, the sequence of partial sums Sn, from n equals 1 to infinity, is 1, 0, 1, 0, 1, 0, etc. That sequence obviously diverges, and therefore the series diverges, right? So this sequence diverges. Therefore, the series diverges. Okay, so it's a divergent series. It doesn't converge to any particular sum. Okay. So moving on. So that's how this definition works, right? Okay, so moving on, let's talk about geometric series. So I'm going to talk about 3 types of series in this section. 3 specific types of series. Geometric series, telescoping series, and then we'll talk about the harmonic series. Okay, so for geometric series, they have the form a times r to the k, right? And notice that our index starts at 0 here. It turns out that that's not actually hugely important, and we'll look at an example to see why it doesn't really matter where the index starts. But this is sort of the canonical version of like what a geometric series is. So it's a sum of the form a times r to the k. Okay. We call r the ratio, or sometimes it's called the common ratio, right? So this is a geometric series with common ratio r. So just to give you a few examples of a geometric series. The series 1 plus 2 plus 4 plus 8. Notice that these are all doubling, so you're multiplying times 2 times 2 times 2. Right? So the common ratio is 2, right? The first term a is just 1, so this is 1 times 2 to the k, or just 2 to the k, right? So r is 2 here. But this is a geometric series. Here's another one, a familiar one, right? This is our friend 1/3, okay, just written out as an infinite series. Yeah, it's 3/10 plus 3 over 10 squared plus 3 over 10 cubed. Common ratio here would be 1/10, right? Not 3/10. Be careful. You're not multiplying by 3/10 to get from here to here. You're only multiplying by 1/10 to get from here to here. And you're multiplying more by 1/10 again, and so forth. So the common ratio is 1/10. By the way, it's called a ratio. It's called a common ratio because if you divide any given term by its predecessor, then the common ratio is what you get, right? Or the other way around. But anyway, so that's that. Okay, and then here's another one. 1/2 minus 1/4 plus 1/8 minus 1/16. This is a geometric series. The signs alternate. We take care of that by just writing it as -1 to the k plus 1, because the first term is positive, right? But then the common ratio is, it looks like 1/2, right? Well, we'll call it -1/2 since the terms alternate, right? So to get from here to here, you multiply by -1/2. To get from -1/4 to positive 1/8, you multiply by another -1/2, right? So the common ratio is -1/2. Okay, so here's a fact about geometric series that is very useful to us. A geometric series, right, sum of a times r to the k, right? Here's the expansion of that series. And here we're assuming a does not equal 0, okay? If a does equal 0, then this is just boring, right? It's just 0 plus 0 plus 0 a bunch of times, and the sum is just 0, okay? But anyway, a geometric series of this form converges if the absolute value of the ratio is less than 1. So in other words, if the ratio is between -1 and +1. And it diverges if the absolute value of the ratio is greater than or equal to 1. So in other words, if the ratio is bigger than or equal to 1 or less than or equal to -1, right? So it converges if this holds, it diverges if this holds. Now, if the series converges, then the sum is a over 1 minus r. Okay, where a is the first term of the series and r is the common ratio. So we're going to prove this thing. So let's see if we can prove it. So our claim is that 0 to infinity of a times r to the k converges to a over 1 minus r if absolute value of r is less than 1 and diverges otherwise. All right, so that's the claim that we want to prove. Let's see if we can prove it. So to prove it, again, we would look at a sequence of partial sums, right? We'd want to look at a sequence of partial sums. And so in particular, let's look at the nth partial sum. So S sub n, right? That's going to be, well, if we plug in 0, then r to the 0 is just 1. So this is a plus a times r to the first power plus a times r squared plus a times r cubed, and so forth until we get up to the nth term, right? And we're not adding up all the terms of the series. We're only going to add up the first n terms, right? Because it's the nth partial term. Now, what would happen if we multiply this by r? If we multiply through by r, well, we would get r times s sub n equals r, well, maybe I'll rewrite it as ar plus ar squared plus ar cubed plus ar to the fourth, and so forth until we get ar to the n plus 1, right? So we're multiplying this thing through by r, okay? And now notice what happens when you subtract these two things, right? If we subtract these two things, we have s sub n minus r times s sub n equals, well, a doesn't get canceled down here, so it comes along for the ride, but the rest of the terms do, right? Well, not quite all of the rest of them. This one would cancel with whatever term comes before, but then you're going to be left with a negative ar to the n plus 1. Okay, so that's kind of interesting. Now, if we want to solve for the nth partial sum, then we could factor out an s sub n. And for that matter, I might as well factor out an a, I suppose, right? I can factor out an a and call it 1 minus r to the n plus 1. And then we can divide through by 1 minus r. Well, okay. Now here's a little detail, right? We can divide through by 1 minus r if r does not equal 1. Okay? Because if r equals 1, then if r equals 1, then this thing is 0, and then you'll be dividing through by 0, which, you know, the universe explodes if you divide through by 0. So we'll say if r does not equal 1, then we can divide through by 1 minus r and get Sn equals a times 1 minus r to the n plus 1 divided by 1 minus r. Okay. So now, remember, the series, we're trying to show that the series converges. Well, the series converges if the sequence of partial sums converges, right? So we want to show that this thing converges under certain conditions. Well, to do that, we would look at the limit as n gets really, really large, right? Look at the limit as n goes to infinity. So let's do that, right? So the limit as n goes to positive infinity of s sub n equals a times 1 minus r to the n plus 1. Oh, sorry, limit. It equals the limit as n goes to infinity of this thing. Now, if r, so we'll say, let's say if the absolute value of r is less than 1, okay, then this is a fraction, okay? And when you raise a fraction to a really large number, you get a really tiny number, right? Like 1/2 to the 10,000 is like 1 over 2 to the 10,000. It's like this goes to 0 is what I'm trying to say, right? So if the absolute value of r is less than 1, then this thing goes to 0. Okay? And you just are left with a times 1 minus 0 over 1 minus r. Or in other words, a over 1 minus r. Okay. So there you go, right? We've proven it, right? If absolute value of r is less than 1, then this limit, then the limit exists, okay, and it's finite, and this is the limit, right? So if absolute value of r is less than 1, then the series converges to a over 1 minus r. If absolute value of r is greater than or equal to 1, or we'll say, here we said that r does not equal 1, right? So we'll say if absolute value of r is greater than, we'll just say greater than 1, then limit as n goes to positive infinity of a times 1 minus r to the n plus 1 over 1 minus r. Well, okay, I guess we should look at a whole bunch of cases, but I'm not going to go through all of the minutia here. Basically, let's say that r is positive, right? So if r is positive and r is greater than 1, then when you raise r to a really big exponent, you're going to get a really huge number. This thing is going to increase without bound. And so, you know, I mean, 1 minus that number would be negative, but then you're going to be dividing by a negative down here. So this thing is just going to go to infinity, right? So if r is positive, so we'll say this equals positive infinity if r is positive, okay? If r is negative and absolute value of r is greater than 1, so in other words, if like r is less than negative 1, then when you raise this to larger and larger exponents, it's going to alternate in sign, okay? So it's going to alternate in sign, and the magnitude of the numbers is going to get larger and larger and larger. So you're going to end up with like a split that looks kind of like that, right? If you were thinking about like a graph of the sequence, right? It would be a split that kind of looks like that. So it's going to diverge. It's not going to go off to positive infinity. It's just going to go crazy and be divergent, right? So I'm kind of getting sloppy and not writing all the details down. But either way, if absolute value of r is greater than 1, then the series diverges. So the series diverges. Okay. So if absolute value of r is less than 1, the series converges to a over 1 minus r. If absolute value of r is greater than 1, the series diverges for sure. What if r equals 1? That's the one case we didn't talk about. Well, if r equals 1, let's look back at the partial sum up here. If r equals 1, then the sequence of partials, well, this would just be a plus a plus a plus a plus a. Okay, so you're just going to be adding a number to itself a bunch of times. And so that's gonna grow without bound. We would say, so if r equals 1, then s sub n, right? S sub n would have to equal n times a, right? Because you would have a plus a plus a plus a n times, actually n plus 1 times, n plus 1 times a. So this is if r equals 1. The sequence of partial, the nth partial sum would be n plus 1 times a. Well, if you take the limit as n goes to infinity, this thing's going to go to infinity, right? So if r equals 1, then the series once again diverges, right? So it only converges if r is strictly less than 1. If absolute value of r is strictly less than 1, then it converges to a over 1 minus r. It diverges otherwise, okay? So that's the proof of this fact. And now let's take a look at some examples of applying that fact. So let's take a look. So we'll determine whether the series converges, and if so, find its sum. So determine if the series converges. If so, find its sum. Okay, so let's do this for this series. We've got the sum from k equals 0 to infinity of 5 over 4 to the k. Okay, so a lot of times with these geometric series, you kind of have to fix them up so that they look like they're in this format, right? A times r to the k. And in this case, that's actually not difficult to do. We can rewrite this as sum from k equals 0 to infinity of 5 times 1 over 4 to the k. And then notice that when you raise 1 to an exponent, you're always going to get 1. So this is really the same thing as saying sum from k equals 0 to infinity of 5 times 1/4 to the k. And there you go, right? You've got something times something else to the k. So it's geometric for sure, and it's easy to identify that a is 5, r is 1/4, right? So we can say since r equals 1/4 is, well, we'll say absolute value of r is 1/4, which is less than 1. So since absolute value of r is less than 1, this series converges. Now, what does it converge to? Well, it's going to converge to the sum s is going to be a over 1 minus r. So in this case, that's 5 over 1 minus 1/4. So 5 divided by 3/4, that's the same as 5 times 4/3. So 20/3. Okay, so it converges to 20/3. All right, so there's that one. Now, I want to show you that it doesn't matter where the index starts. So I'm going to do the same series, but this time starting at k equals 2. All right. That was a very sloppy infinity, but anyways, it's from k equals 2 to infinity. Anyway, based on our work from the previous problem, we already know this thing is going to be the sum from k equals 2 to infinity of 5 times 1/4 to the k. And so we know that r is equal to 1/4, okay? And so we know that the series converges. But when it comes to finding the sum, so let me just write that down. Since, absolute value of r equals 1/4, which is less than 1, the series converges. Okay, when it comes to finding the sum, though, there are a couple ways that you could think about it. So one way that you could think about it is that you could say, well, a is definitely 5, right? So then you could say, well, the sum is going to be 5 over 1 minus 1/4. But something about that is a little fishy, right? Because it's like if this sum that starts when k is 0 is equal to this number, then how could this sum that starts at k equals 2 end up being the same number? And the answer is it's not the same number, because this would be the sum that you would get if the index started at 0. But the index here starts at 2. And so what you have to do is subtract off the first two terms from this series, right? So it would be this minus, if you plugged in 0, you would get 5. And then if you plugged in 1, you would get 5/4, right? So it's the same sum as this first one, but minus the first two terms of that series, right? So that's how you would find the sum there. That's one way that you could find the sum. Anyway, so we know that that's 20/3. I'm just going to punch this into my calculator. 20/3 minus 5 minus 5/4 is 5/12. Right, 5/12. Okay, so that's one way you could get the sum. But here's another way that you could get the sum. You could also say, instead of thinking of a as this number, right? Instead of thinking of a as that number, you could just think of a as what is the first term of the series. And in this case, the first term of the series is what you get when you plug in 2, right? Since that's where the series begins. So if I plug in 2, 1/4 squared is 1/16, and 5 times 1/16 is 5/16, right? So you would get 5/16 over 1 minus 1/4. And then you don't have to subtract off the first two terms. You'll get the same answer here. This is 5/16 times 1 minus 1/4 is 3/4, so it would be times 4/3. And then notice the 4 cancels a 4 and leaves a 4. You get 5/12, right? Just like before. So personally, I prefer to do it this way because I think it's a lot less. It takes less thought, right? Just forget about that, right? All you have to do is remember that in the formula, in this formula right here, S equals A over 1 minus R, A represents the first term, right? A represents the first term of the series. Okay, and so it's a little bit misleading because when you're looking at this, you say, oh, well, A is just whatever number you're multiplying by here. But it's not really that. It's the first term of the series, right? And that still works out here because the first term of the series here happens to be A, right? If you plug in 0, R to the 0 power is 1, A times 1 is A, right? But it's maybe worth writing down where that A is not necessarily that number. A is the first term of the series, right? Where A is the first term of the series. Okay, so if as long as you think of A in that way, you can just pop it into the formula like that, and not have to worry about subtracting off, beginning terms. Okay, so that's what I wanted to point out with that example. Let me give you one more example. Ooh, this is a fun one. Let's do sum from k equals 1 to infinity of 3 to the 2k times 5 to the 1 minus k. Now, at first glance, that does not seem at all geometric, right? It seems like you've got a lot more complicated stuff going on. But again, we can fix this up to make it geometric. So one of the things that we can do is notice that 3 to the 2 times k, that's the same thing as 3 squared to the k, right? Because you would multiply those exponents to get back there. And 3 squared is, of course, 9. So in the next step, we'll make that a 9. The other thing that I'll kind of point out is that we can change the order of subtraction here to k minus 1 as long as we make it negative. So this is 5 to the negative k minus 1. And you'll see why I want to do that here in a second. Okay? Because now I can rewrite this as 9 to the k over 5 to the positive k minus 1. Okay. Now, we haven't quite gotten this into the geometric kind of format, but let's see. The issue is that I've got to get these exponents to match. And so what I can do is factor out one of the 9s. Okay? Because when you multiply these things, this has an exponent of 1, right? When you multiply these things, you add the exponent. K minus 1 plus 1 is k, right? So really, this is sum from k equals 1 to infinity of 9 times, now these exponents match, and so I can call this 9/5 to the k minus 1. Okay, and there you go. Now it's starting to look geometric for sure. just to make this k instead of k minus 1, I can start the index at 0. So I can call this sum from k equals 0 to infinity of 9 times 9/5 to the k, and then it looks beautifully, perfectly geometric. What's more is that you can tell that the common ratio is 9/5, right? So we'll say absolute value of r here is 9/5, and that's greater than or equal to 1, so the series diverges. Okay, so the series diverges for sure. Okay, so that's that. Let's look at another type of problem that you could encounter. We talked about the decimal expansion for 1/3 being 0.33333. So this actually gives us a way to convert our infinite decimals back into fractions, right? So let's find the rational number, or in other words, fraction, right? Represented by 0.784, 784, 784, and so forth. Okay, so 0.784, 784, 784 is really 0.784 plus 0.000784 plus 0.000000784, and so forth. Okay? So so this is 784 thousandths, right? Plus 784, goodness, what would it be? Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths? Okay, but notice, right, here we have 3 zeros, here we have 6 zeros. So on the next one, we're going to have 9 zeros, right? Okay. And what you'll notice is that, see, I'm not even going to continue trying to get this into summation notation, because really all we need to know is, first of all, we need to know what the first term is, what's right here. And second of all, we need to know what the common ratio is. And the common ratio here, the thing that you're multiplying to get from this term to the next term, is 1,000, right? 1,000 times 1,000 is 1,000,000. Okay? 1,000,000 times 1,000 is 1,000,000,000, and so forth. So, so note that the first term is 784 over 1,000, and the common ratio r, I'll say the absolute value of the common ratio r, is 1/1000th, which is less than 1. So the series converges to a over 1 minus r, which is 784 thousandths over 1 minus 1/1000th. And you're welcome to kind of do that in your, oh, actually we could do that in our heads easily, right? Because this is going to be 999 thousandths. 784 thousandths divided by 999 thousandths, you flip and multiply, and you're going to get 784 over 999. Okay? So just to check it, I guess we could say 784 out of 999 is, yep, my calculator's rounding that last digit, but 0.784, 784, 784, 784, and on and on and on. So that's how you can change infinite decimals into fractions, back into their fraction forms, which is kind of nice. Kind of a nice thing to know. Okay, here's another kind of example that you might encounter. So let's find all values of x for which the series converges. And then find the sum. Okay. So let's do this for the sum from k equals 0 to infinity of x to the k. All right. This one's pretty obvious. There's not much work to do. It's obviously a geometric series with common ratio x, right? First term would be 1, right? So this is geometric. With a equals, what did I say? A equals 1, r equals x. So the series converges if absolute value of r, which in this case would just be absolute value of x, is less than 1. Okay, and in that case, it converges to a over 1 minus r, where r is just x. So that's it for that one, right? So find all values of x for which the series converges. These are them, right? The series converges if absolute value of x is less than 1. And then find the sum. Well, the sum is going to be 1 over 1 minus x. So you could do this pretty quick now. It's like, what if you have, so remember, x has to be less than 1. So if you had like 1/2, 1/2 to the k is going to converge to 1 over 1 minus 1/2, which is 2, I think. 1/3 to the k is going to converge to 1 over 1 minus 1/3, which is 3/2, I think, right? So anyway, so that's that one. Let's look at another one, kind of like that. So let's do this for 3 minus 3x over 2 plus 3x squared over 4 minus 3x cubed over 8 and so forth. Okay. It may bother you that the exponent here is k instead of k plus 1, given that the first term is positive. But remember, with geometric series, we usually start our indices at 0, right? So if k equals 0, negative 1 to the 0 is 1, and you get 3, right? Anyway, we need to fix this up to make it look more geometric, though, because in its current format, it doesn't look super geometric. But so we've got this series. Which I can rewrite. I can pull out the 3. And all of these exponents match, right? So I can just call this negative 1 times x over 2 to the k power, right? That's just properties of exponents. That's just how exponents work. Or better yet, this is 3 times negative x over 2 to the k power. So this is clearly geometric. It's geometric with common ratio negative x over 2. So this is geometric with first term 3 and common ratio negative x over 2. It converges if the absolute value of the common ratio, so if the absolute value of the common ratio is less than 1. Well, that implies that, first of all, the negative is not going to matter when you take absolute values, right? So this is just absolute value of x over 2. In fact, you could kind of write it that way. And that's kind of silly because absolute value of 2 is, of course, just 2. So you can multiply both sides by 2. Get absolute value of x is less than 2. All right? So in other words, if x is between negative 2 and positive 2. So this series is going to converge as long as x is between negative 2 and positive 2. In that case, it converges to a, which we said earlier was 3, over 1 minus r, which we said is negative x over 2. So that's 3 over 1 plus x over 2. If I want to clear that complex fraction, I can multiply through by 2 over 2 and get 6 over 2 plus x. Okay. So that's it for geometric series. Now, probably half an hour ago, I said that we were going to talk about 3 types of series: geometric series, telescoping series, and harmonic series. But telescoping and harmonic series aren't going to take as much time. I just have one example to show you for a telescoping series. But the following series is telescoping. So let's determine whether this series converges, and if it does, let's find its sum. So we have 1 over k times k plus 1. Our index is starting at 1. Okay. Okay, so this one is not geometric. This is not a geometric series. This is what we call a telescoping series. And you'll see why as we go through this example. One over k times k plus 1. Okay. So the first thing I'm going to point out is that if we were wanting to integrate this thing, we would probably use partial fractions, right? And we'll see later on in this chapter that integration and summations really kind of go hand in hand. I mean, that's something that you should kind of have an intuitive understanding of anyway, because an integral is just a summation, that you allow where you allow the number of rectangles to go to infinity, right? It's that sort of notion. So anyway, so I'm going to use, maybe it's useful to write out the first few terms, I suppose. But, this would be, if we plugged in 1, we would get 1 over 1 times 2. If we plugged in 2, we'd get 1 over 2 times 3. If we plugged in 3, we would get 1 over 3 times 4, and so forth. Which looks very similar to a problem that you had in the homework that I just looked at on the discussion board. But anyway, let's use partial fractions to break this down, right? So I know that 1 over k times k plus 1 equals a over k plus b over k plus 1. So that means 1 equals a times k plus 1 plus b times k. So this is a pretty easy one. If we plug in 0, b goes away, and we just get a equals 1. If we plug in -1, the a goes away, and we get 1 equals negative b, so b equals negative 1. Okay, so this sum, 1 over k times k plus 1, equals the sum from k equals 1 to infinity of 1 over k minus 1 over k plus 1. Now, why did I want to do that? Because check this out, right? So now if you expand this series, you're going to get, if you plug in 1, you get 1 over 1 minus 1 over 2. And if you do the next term, you get, if you plug in 2, you get 1 over 2 minus 1 over 3. And if you do the next one, you get 1 over 3 minus 1 over 4, and so forth. And what you'll notice is that the negative 1/2 and the positive 1/2 will cancel. The negative 1/3 and the positive 1/3 will cancel. So what I should actually do is look at the nth partial term. So the nth partial term is going to be 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, and so forth, until we get to 1 over n plus 1, right? So 1 over n minus 1 over n plus 1, right? That's the nth partial sum. And for the nth partial sum, all of these things cancel. The 1/2 and the 1/2, the negative 1/3 and the positive 1/3, the negative 1/4 and the positive 1/4, right? And so forth. The term that comes right before this one is going to have a 1 over n here that's going to cancel a negative 1 over here, 1 over n here that's going to cancel the positive 1 over the n there. But then there's going to be nothing to cancel that negative 1 over n plus 1 on that last term. But anyway, so this is just going to end up being 1 minus 1 over n plus 1. That's the nth partial sum. So now if you look at limit as n goes to positive infinity of the nth partial sum, as n goes to infinity, this thing goes to 0, and so you just get 1. Okay, so you can say the sequence of partial sums converges to 1, therefore this series converges to 1. So the sequence of partial sums converges to 1, therefore the series converges to 1. All right, so that's how telescoping series work. So they're kind of fun. You usually do this trick where you do partial fractions. You look at the nth partial sum and look at the limit as n goes to infinity of that nth partial sum, and that'll tell you if it converges or diverges. And it'll also tell you what it converges to in the case that it does converge. So those are kind of nice. The last type of series that I wanted to talk about in this section is the harmonic series. So the harmonic series is this series right here. It's the sum of 1 over k as k goes from 1 to infinity. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so forth. If you add these things up, this is what's called the harmonic series. And it might surprise you that the harmonic series diverges. And the reason I think that's maybe a little bit surprising is because as you go out, the terms get smaller and smaller and smaller. And so you might think to yourself, well, I keep adding smaller and smaller and smaller things, so certainly this is going to approach some finite value, right? But it doesn't. And I'll show you why. So I'm just going to walk you through kind of a sketch of the proof that this thing diverges. But first of all, note that the sequence of partial sums, S sub n, is strictly increasing, right? So S1 would just be 1, S1 would be 1, S2 would be 1 plus 1/2, S3 would be 1 plus 1/2 plus 1/3, and so forth. And this sequence, S1, S2, S3, S4, it's strictly increasing because you keep adding values to the previous term in the sequence. All right, so it's a strictly increasing sequence, and it has no upper bound, right? So this sequence has no upper bound. Now, this fact is a little bit more difficult to see, but let me show you why this has no upper bound, okay? So notice that S2 is 1 plus 1/2. That's greater than 1/2 plus 1/2, and you might think, well, why do I care about that? But you'll see the pattern here in a second. So this is greater than 1/2 plus 1/2, which equals 2/2. So S2, whatever S2 is, it's bigger than 2/2. S4 equals S2, 1 plus 1/2, plus 1/3 plus 1/4. And now that is greater than S2 plus 1/4 plus 1/4, right? 1/3 is bigger than 1/4. So this thing is bigger than this thing. Now 1/4 plus 1/4 is 1/2. S2 we said is greater than, so actually I should fix this. This is greater than S2 is greater than 2/2. So S4 is greater than 2/2 plus 1/2, which is 3/2. Okay? S8 is whatever S4 is plus, right, S4 is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Now what are we going to do? We'll take all of these fractions and make them 1/8, right? These are all bigger than 1/8, so this sum is bigger than this sum, right? But the nice thing about making them all 1/8 is that now if you add up 1/8 plus 1/8 plus 1/8 plus, that's 4/8, or in other words 1/2. So this is S4 plus 1/2. S4 we said was greater than 3/2, which means that S4 plus 1/2 is greater than 4/2. Okay, so you can kind of see how this is going, right? If we doubled this index again to 16, we could show that S sub 16 is greater than 5/2. And then we could show that S sub 32 is greater than 6/2. And that S sub 64 is greater than 7/2. And no matter what number you give me, I can always go out far enough in this sequence so that my sequence is going to be bigger than that number, right? So consequently, S sub n has no upper bound. So we have this sequence that's strictly increasing, but that has no upper bound. And you may recall from the previous section that an increasing sequence with no upper bound diverges. So the sequence of partial sums diverges, and therefore the series diverges. So the harmonic series it's just one series. It's an interesting series, but it diverges, right? It diverges. So that's kind of an interesting fact. And that's all I have to say for this section. I've been talking for quite a long time anyway.